So we are going to start. The first speaker is Professor Jan Rückmann from the University of Bergen in Norway, and the title of his talk is MPCC, a strong stability of quickly non-degenerate stationary points.
Okay. Thank you very much, Lola. Thanks for coming. And I was here several times already in the past, and my lecture today is in some sense a continuation of other lectures. So I will present some stuff I already presented and some new stuff. And when I start here, this is the outline, introduction, notations, and so on. Let us define what we are talking about. We consider the class of mathematical problems with complementarity constraints, so everybody is familiar with this stuff, I guess. And let's see how that works now. You can see it, but not here. Okay, the point is here in red. This is a difference to the standard problem, and we have this structure of a minimization of pairs of constraints here, finitely many, and since we are talking about stability properties, we define the problem as depending on the objective function f. What happens now? On the objective function f, and then the corresponding constraints, and that means stability means what happens if we are changing, perturbing a little bit the set or parts of the set of functions. Some comments here, which we will not go into details too much. We skipped all the, let's say, finitely many standard equations and inequality constraints. We concentrate on this complementarity constraint property. And also, if I perhaps make you some kind of small picture, if you have a pair of functions x times y is equal to 0, then it is obvious that we have both are greater than or equal to 0. Then locally, this is our feasible set. And the interesting point is, of course, here. Yeah, there where the differentiability properties are destroyed. Okay, so if we are at the point here, which means only one of them is active, at least one must be active, obviously, because it leads to 0. But here are both active, and if we are here or here, then locally, this is like a standard optimization. Yeah, so there's an interesting point for stability, for structure properties, and so on, is this point, when both are equal to 0. Okay, strong stability, I will define it, refers to existence, uniqueness, and continuity. Continuity with respect to perturbations, so it means small perturbation, the smaller should be the change in the structure of the solution set of the problem. The challenge is always, as we know, that we can define strong stability to say, okay, existence, uniqueness, continuity should be fulfilled, but this is a property which cannot be handled. We cannot check this. Yeah. So then the question is, how can we formulate conditions which we can check? And one thing is an algebraic characterization. Kojima did this in the 80s, the first time for standard nonlinear optimization problems. And I will come to this definition later on. So here's this little bit historical view for NLP as nonlinear programming. That means finitely many equations, finitely many inequality constraints. And what he did, that is what Kojima really did, is besides the topological definition, the existence, uniqueness, and continuity, he presented an equivalent algebraic characterization. It forms the first and second order derivatives of the involved functions. And then there was a generalization to semi-infinite programs later on. And also, Kojima did this under linear independence. and also under Mangelson-Formalist constraint qualification and without linear independence. And later on, then 2006 and 12, it was shown one needs the Mangelson-Formalist constraint qualification in order to get strong stability. Okay, and what we will do now here is in blue, the last two lines, algebraic characterization of strong stability. And now comes the difference, another difference into play, namely when we have for nonlinear programming one stationarity concept, stationary point, very well known. We have several of these for NPCCs. As here, what we are talking about now in the follow is about M stationary points and S stationary points. There are other concepts which can also be defined, and we will look at the concept of weak non-degeneracy. I come to this later. Okay, some notations and basic results. This is technical stuff which I will not go into details here. What we did in this paper, I showed the paper in the first slide. It was sign optimization. We can describe stationarity concept by using a generalized equation. It is in blue here. So it means instead of minimize a function and so on, we can say find a point, and this is some kind of like a Tucker condition. On the left-hand side, we have the gradient of the objective function. These are the gradients in general of the constraints, and the theta is from capital theta taken, and this refers to the definition of the stationarity. Different stationarity concepts give us different thetas. And the thetas is a cone-valued mapping, which can also be empty. So we can define it for each point. Doesn't matter if it's feasible or not feasible. Okay. And then we can define our problem under consideration, where the theta comes into play here. It means depending on which stationarity concept do we want, then the corresponding theta we can choose accordingly. Okay. And then when we have this, then of course we can use all the machinery we know. For strong point, stationary point, Lagrange multiplier, or Lagrange vector, we call it, which is given here. And so we can handle several stationarity concepts by using this formulation, including the theta. Okay. The same thing, or an anomalous approach we can do for the constraint qualifications. We can say we can define the so-called generalized linear independence constraint qualification and the generalized Mangelson-Formalist constraint qualification. And we see the definitions here. Also, GLICQ is defined as this: the intersection of the kernel of the gradients of the constraints. And here we have the span of this cone-valued mapping, and LICQ or GLICQ is fulfilled if this intersection is only 0. Important is this. Yeah, I had also to look at this. The span of the empty set is 0, the smallest subspace. Yeah, and the little bit weaker condition, the generalized Mangelson-Formalist constraint qualification, is set to hold if it is contained here. So we do not have the span here. That's why it could be empty as well. Yeah, it's empty or it's 0. Okay, what is that now here? Okay. Yeah. And we see, what is that? Okay. So again, let me say it again. Yeah. As we have here now generalized the notion of the constraint qualification, GLICQ and GMFCQ. And of course, we have that for the nonlinear programming problem, for a standard problem, this is exactly our LICQ and MFCQ. Yeah, otherwise it would be strange, of course. And we also can define this, the GMFCQ, for any point. That means we have that the cone value mapping is empty when we are in a point which is not feasible. So we do not care about is it a feasible point, not a feasible point. We can always go with this GLCQ or GMFCQ. Okay. So then we define here some topological stuff. How magnetic if we are looking at perturbations, then of course we have to say what is meant, how to measure them, and this is technical. Okay, now let us define, or taking over from Kojima, or generalize this definition of Kojima, strong stability. And you see it here. So we can perturb the problem in a neighborhood in such a way that we have this condition here. So sigma of P is the set of stationary points, depending on the concept. We will not distinguish now. And we can say strongly stable, this small super index S here. Okay, so the second speaker already knows. Okay, so when we say for each sufficiently small to the problem, we have locally around this strongly stable solution, we have exactly one solution, uniqueness, existence, and it depends on the perturbation. So we have the measure, we define the measure, how to measure perturbation, and then we have that. I will not go into details here for weakly stable, but the difference between strongly stable and weakly stable is here the theta is varying between 0 and a certain theta bar, and it should hold for all theta in this interval. And so that means we can make it small or big, but we have only exactly one solution for the perturbed problem. Weak stability means we leave the theta bar fixed, and we do not care about smaller thetas here. Okay? And this is now what Kojima did for the standard optimization problem. He gave this equivalent topological characterization. And what is he saying here? We have two conditions which are equivalent, namely strong stability, sigma S, as a X bar is strongly stable, if and only if for all Lagrange multipliers from the extremal set of the set of Lagrange multipliers, which we know is a polyhedron, and we only take the corners. Yeah, and the corners we define a condition, namely that the Hessian of the Lagrangian respected to the corresponding tangent space is positive definite. This is what Kojima did, and when we now ask the question, what can we generalize for MBCCs here, then there is one condition here, which we will see has to be generalized as well. Namely, here we are talking about the set of Lagrange multipliers, which is a polyhedron, and take the extremal points. It's a convex set. Okay. We will see later that the set of Lagrange multipliers is not convex. So we cannot talk about extremal points there. And then the question is, what are we doing then? We will see what will be the answer. Okay, so some technical stuff here. This is referring to my picture here a little bit. So as the interesting set is the last one, when both for a pair of constraints R1 S1, for example, when both are 0. Yeah, this is a set which is interesting for us. If we are here, where exactly one of the two are active and but the other not, that means we are here or here, but not in this corner point. yeah, it's not interesting. Okay. Let us recall M stationarity and S stationarity, because if you remember, we looked at generalized equations to characterize different stationarity concepts. So let us look what does it mean for these two stationarity concepts here, M and S stationarity. You see the definition here, that's the Lagrange multiplier, the Lagrangian. This is a standard that the first derivative with respect to x is equal to 0. We have some complementarity constraints here. And then the blue, you see in blue here and there, this is a difference between M stationarity and S stationarity. And the rest is the same. Okay. So M stationarity means that the corresponding rho and sigma are positive, or at least one is 0. And here we have that both are non-negative. This is the orthant. Here it's a little bit more S stationarity. And let us look at the description of M stationarity using this generalized equation. Different stationarity concepts, I stated already, refer to different Cohn-Bendit mappings to this capital theta. Okay, and what does it mean here for M stationarity? Analogous for S stationarity, but we make it here only for M. So that means what we have to do when we use this generalized equation approach is to define how does this capital sigma, capital theta Cohn-Bendit mapping look like. And we see it here now as a theta n, and refers to, then refers to M stationarity. You see it here, how this condition comes into play, the condition which defines M stationarity. And this set here is defined like that. So that looks very technical. Of course, you cannot cut this immediately. But the interesting thing is here that this capital theta M is a closed set where theta S is not closed. Of course, that has some consequences for proofs and so on when we are looking to different descriptions using generalized equations. Okay, and here are some conditions. The generalized LICQ for both M and S stationary point is, of course, equivalent to the condition MPCC LICQ. That means standard that all the active constraints have form a set of linear independent derivatives. And there's another consequence here that MFCQ implies SMFCQ. So what does it mean, MFCQ and SMFCQ? Remember, we had definitions, generalized definitions of the constraint qualifications. And we, when we write this down for a concrete, particular stationarity concept, then for that, if we are looking at M stationary points, then this definition is M, refers to M Mann-Sein from its constraint qualification, and also to S MFCQ. And we also see that the set of Lagrange vectors fulfills this inclusion here. And we can also show that the M, respectively S, Mann-Sein from its constraint qualification are necessary conditions for strong stability. Okay. Now let us look at this strong stability and also look at this concept of weak non-degeneracy. Here's a definition of weakly non-degenerate point. Perhaps you remember what does it mean non-degeneracy in the standard way. In the standard way, it means we have complementarity constraints, complementarity conditions that all the Lagrange multipliers are non-zero. And we have also some kind of second order condition about the Hessian of the Lagrangian restricted to the tangent space. Now we say the following. This is here IRS, where the set of indices which belongs to those pairs which are equal to 0. Yeah, so it means they have corresponding multipliers, and weakly not degenerate means both of these multipliers for any index from IRS are equal to 0. So we exclude the case when we say weak non-degenerating. We exclude the case that we have multipliers 0, 0. And this is excluded. And okay, then we have the following conditions here as well. As this S refers to S stationarity. The set of corresponding Lagrange vectors is convex. Remember, convexity played an important role in the condition Kojima presented, because we use this polyhedron and the corner points, the vertices. But if we look at the M stationarity, here big in red, this is not convex. So the question is then, what are we doing with this when we want to formulate second order condition for strong stability? And it is not convex. It is not, has no extremal points, because extremal points are only defined for convex sets here. And what we did then finally, we found a substitute for these extremal points, and we called it basic Lagrange vector. The definition is here. So it means an element from the set of Lagrange multipliers is called a basic Lagrange vector. As I always have in mind, this is a generalization of the extremal points of the corner of this polyhedron. If there does not exist another element from the set of Lagrange vectors, which of course should be different to the basic Lagrange vector, and it should have this condition here. So if you look at the condition, you see that we are only interested in those from this index set. This is the picture I made at the very beginning. And that said, there's no sigma 0 such and rho 0 such the set of the star set is a set of indices which belong to non-zero multipliers, which is a subset of the non-zero multipliers of these non-existing Lagrange multiplier. And so this is some kind of generalization of an extremal set, of an extremal point set, but it's different, and it can be done for any need not to be convex. So there's a point here. Okay. Okay. The question now is that, remember, the set of Lagrange multipliers for S stationary points is convex, but this is not convex in general. And the question is now, where's the relationship between these two things? Can we use this relationship in order to look at the extremal point set for this convex set? Where's the relationship? Here's S, and here we have the M stationary point set. Okay. So then, of course, you can prove several properties here, and we have here in red that this latter condition imply that these two sets are equal, and it is shown in the next example. I will skip the example here. I have several other examples, but 35 minutes. Do I have 9 minutes more?
Yes.
Yeah, okay. Okay, so if we are talking now about, instead of extremal points, of basic Lagrange vectors for non-convex sets of Lagrange vectors, then the question is, yeah, can we say something about the existence? When we formulate a condition for basic Lagrange vectors, then the question is, are there any basic Lagrange vectors? And this is here formulated in this statement. The blue says there exists a basic Lagrange vector. No, LB was the set of basic Lagrange vectors here. If and only if, and then there is a condition which says something, if and only if condition for the existence of Lagrange vectors. Okay, now we come to the Mangasal formal constraint qualification for n stationary points, and we are talking about the necessary condition for strong stability in this setting. In this chapter 4 here, we assume that we are looking at a weakly non-degenerate S stationary point. Remember that what it was, a weak non-degeneracy, but it was a concept we introduced here. And that means there it's not possible that the pair of Lagrange multipliers is both on 0. Yeah? This is excluded. And the idea, that is 2000 von Scheel and Stefan Scholtes, he looked, or they looked at a relaxed problem. Relaxed, originally it was a problem with complementarity constraints. And then they looked at a relaxed problem, which is defined here. Perhaps one comment on this, of course, in this time, at the end of the 90s, beginning 2000, the question always was how to solve problems with complementarity constraints. And it means how to look at corresponding nonlinear standard problems, problems with equality and inequality constraints. So this is a little bit other context where it was introduced. Now we use this for our setting here. And the point is here, if you look at this problem, I come back, then you see that the second point here, this relaxed problem does not depend only on the functions describing the problem, but also on those describing the problem at the point x bar. So what does it mean? If we go back, you see that the index sets which define the corresponding constraints depend on x bar. So that means if we change, if we change okay, here, if we change the point x, these index sets may change, and then the problem is changing. Yeah, and so it is not fixed. Yeah, it depends on x bar and of course on the functions, and you see that here. And the good or the interesting point for us is here that the set of Lagrange multipliers of this relaxed problem, of this standard nonlinear program, is equal to the set of Lagrange multipliers of the problem with respect to S stationary points. So this set is convex, obviously, because it is equal. And this is a standard problem. We have here a convex set, polyhedron. Yeah. One of the consequences is formulated here in this lemma. Assume that the S Mangasal formal constraint qualification is fulfilled at the considered point. Then we have blah blah blah, and the blue one is this here, namely that the set sigma is a set of stationary points of the relaxed problem locally is a subset of the stationary points of the problem with respect to S stationarity. And this inclusion can be strict, which is in the next example. So strong stability does not imply strong stability of X bar for this problem. Okay, I skip the example. And we have then here the following theorem. Here I have a superindex W. I didn't explain this because I didn't want to put too much technique here into this lecture. Weak stability. And the theorem says, assume that we have S MFCQ at the considered point. And if we have weak weak stability, either for PS or PM, then X bar is the strongly stable point for the relaxed problem. Okay, so here's another connection between the nonlinear standard relaxed problem and our complementarity constraint setting. And we have, and this is now interesting, that these two sets are equal. Remember, one was convex, and about the other we couldn't say anything. But under these conditions here, they are the same. So that means that one's convex and both are convex. Okay. Another problem and another example here, the boundedness does not imply MFCQ. This is, of course, the big difference to the nonlinear problem, namely, there we know MFCQ is equivalent to boundedness of the set of Lagrange multipliers, 1, 50s. And this is shown here in this example. That is not the case here. Okay, and I will skip a little bit here. Now here, I have 2 minutes.
Yeah.
Then let me come to the end. Topological and algebraic characterization of strong stability. So here is topological characterization. The following 3 conditions are equivalent. Strong stability with respect to S stationarity is equivalent to strong stability of M stationarity. And we have this condition here where MMFCQ comes into play and where these both sets are equal. Yeah, so that answers the question we formulated. What can we do if we want the set is non-convex? This is not possible in the strong stability. Okay. And now the algebraic characterization. So before it was topological, it will only say existence, uniqueness, continuity. Now we use algebraic characterization here as well. Assume MFCQ, but not MPCC LICQ. This was done by Vladimir for the case LICQ. When was it? 2014? Yeah. 12, okay. Then the following 5 conditions are equivalent. We have, again, strong stability for S and for M stationarity. And then we have here a similar condition, which we know already. The Hessian of the Lagrange restricted to the tangent space should be positive definite. I will not go here in all the definitions, but the point is again that we have that these 2 sets are equal. One was clearly convex. On the other thing, we couldn't say anything so far, but now we know they are both convex. And then we can, of course, talk again about extremal points. For a convex set, we can that define, and we can say if it is a polyhedron, then how the vertices. Okay, and when we get this, or 2 other formulations which are here given as well. Yeah, okay, 35 minutes. Okay. Thank you very much. Any questions?